from the work energy principle, we said that any external work done on a system would change the kinetic energy of that system. So we're looking at forces from outside affecting our object in our system. And we've seen how gravity and springs can perform work on an object. We've seen the work done by force of gravity is force times distance. Since gravity is only vertical, we only care about vertical distance. And since gravity is essentially constant, we can basically do force times displacement. When we look at the work done by a spring, the force of a spring is not constant, and so we had to integrate from an initial position to a final position to find the work done by the spring. And in either case, these works are taking kinetic energy away from our object. They're taking kinetic energy away because they're applying forces that are slowing our object down. But instead of treating these as external forces that are acting on our system from the outside, we can fold them into the system and include them as part of the object's energy. We do that by defining them, defining the work done as negative change in gravitational potential energy and as a change in elastic potential energy. What this means is that if gravity is doing work to slow down our object, if gravity is doing work and is taking kinetic energy away from our system, that energy doesn't disappear. That energy goes into gravitational potential energy. If the object begins to fall again, gravity will start doing positive work on the object. If gravity is doing positive work, we're losing gravitational potential energy, but that work is going to increase the kinetic energy of the system. So we're losing gravitational potential energy, but we're gaining that kinetic energy back again. The same is true if we do work to compress a spring. We lose energy of the block, but we gain energy of the spring. If we were to release the spring again, the spring would do positive work on our block. That would mean we would lose spring potential energy, but we would gain kinetic energy back into the system. And so then we're looking at an exchange of energy that's all occurring within the system rather than looking at the outside world influencing our system. In each case, we took an external work that was done and we defined it as a negative change in a potential energy. So that positive work that increases the kinetic energy comes from a loss of potential energy. Negative work that would take that potential energy away. A negative would be a positive change of potential energy. Basically, in that situation, you're taking kinetic energy away and putting it into potential energy. In that case, our work energy theorem becomes a change of potential energy is negative change in gravitational energy, negative change in spring or elastic potential energy. In that case, we can move both of these across the equal sign. The negatives will become positive, and we have a new equation here where the change in the kinetic energy plus the change in the gravitational energy plus the change in the elastic potential energy equals 0. Because we've taken the external forces acting on our object and we have folded them into the system and included them as part of the system. When we expand this, we can say the change in kinetic energy is the kinetic energy final minus kinetic energy initial. Our change in gravitational potential energy is from the change in the height, and the change in the spring potential energy comes from the change in the compression or extension of the spring, and all of this still equals 0. But what we can do, we can rearrange, instead of treating everything in terms of the type of energy, kinetic, gravitational potential, elastic potential, we can treat them in terms of the final values or the initial values. And so we can separate them, put all of the final values together, and put all the initial values together. And what we see is we have all the final kinetic energy, final gravitational energy, final spring energy equals the initial, or that the energy, the total energy at the end, would equal the total energy at the beginning. Perhaps those total energies are in different forms, if there's been an exchange of energy, but the total amount of energy is equal to zero because there are no more external forces, because we've brought all those external forces into the system and included them as part of the system. So this is the relationship we just determined, that the total energy at the end is equal to the total energy at the beginning, and the end and the beginning are arbitrary points along the evolution of the system as well. That if you consider a system that's evolving with time, you could consider its total energy at any two arbitrary points in time, and the total energy of the system would be the same in both of those cases. While this is a little more complex, what we're concluding from this is that for a system with no other interactions, no external forces, because we had external gravity, we had external spring forces that we wrapped into the system. We're saying no other external forces on top of that. In that case, when we have no external forces, no interactions with the environment, the total energy of the system does not change. So the energy can be transformed in many ways, but the total amount of energy does not change. We can also include thermal energy of the system. When we're looking at the thermal energy of the system, we're looking at the interaction between the surface, presumably that the object is moving on, and the object itself. And we know that the change in thermal energy comes from the work done by the force of friction. When friction is doing work, that energy is taken away from the kinetic energy of the object, and it is turned into kinetic and potential energy at a nanoscale, a microscopic scale, within the object and within the surface. When we wish to include that into this energy principle that we've been discussing, we have the total energy at the beginning, and we have the total energy at the end, and we have to include this change in thermal energy that occurs in the process, that occurs during the time between the initial point in time and the final point in time. In this case, mechanical energy, which is defined as the kinetic energy and potential energy, it's not conserved if there is friction. The mechanical energy is not conserved because some of the energy, mechanical energy that is there, ends up as mechanical energy, but some of the mechanical energy ends up going to friction as well. So the mechanical energy at the end is less to account for the energy that went to allow for the energy to have gone to overcoming friction. We also know that the change in thermal energy is always greater than zero. Friction always makes objects hotter and never colder, and so the final mechanical energy always has to be less. When we include all of these ideas together, we come up with the conservation of energy. When we look at the total energy of a system, which is the mechanical energy of the system as well as the thermal energy of the system, we can say that if it is an isolated system, then the total energy is constant. An isolated system here means no external forces beyond gravity and spring forces and frictional forces, all of which we've included here. The kinetic, potential, and thermal energies within the system can be transformed from one into the other, but the sum cannot change because if it's an isolated system, the total energy is constant. If the system is both isolated and non-dissipative, which means that the force of friction is equal to zero, we're not including friction, in that case, the mechanical energy of the system is conserved, meaning that there's no loss to thermal energy, and the total mechanical energy, which is kinetic and potential energies, will be the same at any given time. Not necessarily the same amount of kinetic versus potential energy, but the same total energy. Here we see a cartoon of this idea of the conservation of energy at work. When you have a system that's isolated, the total energy of the system is constant. So in this case, we have a system, and the system is isolated from the outside world. You have kinetic energy, which is your motion, and you can also have potential energy. That potential energy can be gravitational potential energy, and it can also be spring potential energy. You can have an exchange of energies between kinetic and potential energies, and as there are losses in the system, as there is friction, for example, some of this energy gets turned irreversibly into thermal energy, into the heat of the system. While there's an exchange between all of these values, the total energy of the system is not changing. Another way to visualize this exchange of energy between kinetic and potential energies is to use energy bar charts. For example, here a ball is tossed up in the air. We know that the ball is going to be going fastest as soon as it's thrown. It slows down as it gets higher up. At a certain instant, its velocity is 0, and then it begins to accelerate downward, and when it hits the ground, it's going as fast as it was when it began. In this situation, if we want to treat it as energies instead of considering it as velocities and the acceleration due to gravity, we have to consider the velocity as being representative of the kinetic energy. We also need gravitational potential energy. Since it's an arbitrary to pick a reference point for gravitational potential energy, it makes sense to pick the ground to be our 0 gravitational potential energy line, and we'll count gravitational potential energy above the ground as being a positive amount. So if we look at the initial position, the ball has 0 gravitational potential energy because it's still on the ground, but it has, and all of its energy is kinetic energy. We see that in the energy bar chart as well, that all of the energy is kinetic energy, none of the energy is gravitational energy. As the ball goes upward, its gravitational potential energy goes up because it's higher off the ground, so it has a larger gravitational potential energy. But it's slowing down, and so its kinetic energy is less. When we look at the total of the 2 bar charts, we see that the total line of energy that we have, if we add the 2 energies, we still reach the total amount. But the energy is half kinetic and half gravitational potential energy at this point. Later on, the ball is motionless for an instant. In that situation, the kinetic energy is 0, and all of its energy has been converted to gravitational potential energy. As the ball begins to fall back down, it still has some gravitational potential energy, but it's gaining speed, so it has a little more velocity and has kinetic energy. It doesn't matter what direction the velocity is in because the kinetic energy is 1/2 mv squared. And then as it hits the ground, it has 0 gravitational potential energy, and so all of its energy is back to being kinetic energy. And so using these energy bar charts, we can see the total amount of energy and see how the total energy is distributed amongst kinetic energy, gravitational potential energy. Here we're flying through the air, so there was no friction, there was no thermal energy for us to consider. There are no springs in this situation, so there was no spring potential energy for us to consider. But in a more complicated system, we could have multiple bar charts, including all of those different possible contributions to the overall energy of the system.